Okay. So yes, we call the number b inverse of a if this is satisfied. And so this intuitively comes from the fact that we see with regular equal signs. So we have maybe an expression in regular math like 3 divided by 5 is equal to 3/5. But if we wanted to do this in modular arithmetic, we can't usually use the division because remember, we're only using remainders here. So instead, we would do 3 multiplied by 5 to the negative 1 to get an equivalent modular representation of this type of like division. And also, this 5 to the negative 1, usually when we divide by 5, what we're doing is really 3 times 1 over 5, or 5 to the minus 1. And 1/5 in regular math times 5 is equal to 1. And this is the same thing we see here. So that's how we motivate our definition for a multiplicative inverse inside modular arithmetic. But we also have to look at when inverses actually exist in modular arithmetic, because for instance, with the numbers, let's say 8 and 8 mod 15, if we want to find an inverse, a number such that when we multiply that number by 8, we get 1 mod 15, we can see that that number would be 2, because 2 times 8 is congruent to 16, and 16 is congruent to 1 mod 15. So in this case, 2 would be the inverse to 8. However, with another example, like let's say 5 mod 15, you'll never find a number where you multiply it by 5 and you get 1 mod 15, because 5 is a factor of 15. And so we want to find a general way to describe when there are multiplicative inverses to numbers. And to do that, we're going to introduce a quick theorem known as Bezout's identity. So Bezout's identity, it's a theorem that can be proven with construction and some arguments actually. But it states that for two positive integers a comma b, we know that there exists two integers x and y, so these are integers, such that a times x plus b times y is going to be equal to the greatest common divisor between a and b. And so this is what Bezout's identity states. And it basically just, it doesn't tell you how to find x and y, but it'll tell you that there exists an x and y when you do this. And so if we look at our definition of an inverse, we need some number a times b to be congruent to 1 mod n. So we can actually use the definition of a congruence to write n divides ab minus 1. So we can actually write ab is equal to n times k for some integer k plus 1. And if we just rearrange this, we can get ab minus nk equals 1. And hopefully you can see that if we take our a and b here, we're not using the same a and b, but essentially the two numbers we're using are this number and this number. So we know a and n. So we know by Bezout's identity that there exists this value here, this b, and there exists this k, both integers, where this is true. And because of Bezout's identity, we know that this 1 would be equal to the greatest common divisor of a and n. So when this condition is satisfied, we call a and n as relatively prime or as co-prime. Essentially, they share no common factors with one another. And so that's going to be our condition for when an inverse exists. So you can write that there's a theorem, we've just proven it, that if two numbers a and n are co-prime, then there exists an inverse of a. So inside mod n. Okay. Essentially, this theorem basically tells us when this exists. And actually, if we look at Bezout's theorem, we actually get a hint as to how to compute a to the minus 1. Because we know that from our equation here, we have that ab minus nk is equal to the GCD of A and N. And so if we use our common Euclidean algorithm with the numbers A and N here, so we start off with A and N and we subtract multiples of A and N from each other until we get their GCD, which is equal to 1, we can reverse that and find the coefficients on A and N, which would be B and K. And finding that B would allow us to find what the inverse is because of how we define the problem. So I explained this more in detail in our introductory lecture. So if you missed that, you can go watch that on YouTube later. So we've talked about inverses now, and actually, let's talk about one more thing regarding inverses. Because we have inverses now, we're actually able to solve equations such as maybe ax plus b is congruent to c mod n. So this is called a linear congruence. It's like a linear equation, but with congruences. So we can actually solve this if a and n are relatively prime, because we have that ax is congruent to c minus b. And if we multiply each side by the inverse, a to the minus 1, so we multiply a to the minus 1 to each side. Then we have, because a to the minus 1 times a, this expression is congruent to 1 mod n by the definition of an inverse. We have that x is going to be congruent to a to the minus 1 times c minus b mod n. So we're actually able to solve any given linear congruence as long as the coefficient of x is relatively prime to whatever our modulo is. Now we're going to go over a very quick theorem. If a and b are congruent to each other modulo n, then we have that the GCD of a and n is equal to the GCD of b and n. And so we can approach this, we can prove this using our definition of a congruence, because when we write a is congruent to b mod n, what we're really saying is that n divides a minus b, or that a minus b can be written as a multiple of n. So let's pick some integer k, where a minus b is equal to n times k for some integer k. And so we can write then that a is equal to nk plus b, essentially a remainder of b when divided by n. So we substitute this into our first GCD right here. So GCD of a and n is going to be equal to the GCD of nk plus b comma n. And when you've learned what GCD is, and we've learned Euclidean algorithm from previous lectures, we know that we can subtract one of these values from the other value until there's a remainder left. So if we just keep subtracting n until we get rid of the nk, what we're left with is GCD of b comma n, using the Euclidean algorithm here. And so that's how we prove that these two values are equal. And so this is going to be a fact that we're going to be using for an example that's coming up. And so here's an example, and I'm going to quickly explain it. So for an odd positive integer, n is greater than 1, let the set S be the set of integers x, where x is in this range, it's between 1 and n, such that both x and x plus 1 are relatively prime to n. And then we want to show that this product congruence here is true. So in case you've never seen this product symbol before, essentially what it means is it's just like a sigma when you do sums, but it's for multiplication instead. So for instance, in this example, we're saying for all x in the set S, and we're going to multiply these x. So essentially, for example, let's say our set was 1, 2, and 3 in S. Okay, so this is an example. Then this product would just be the multiplication, like the product of all of the elements in the set. Because for every element x in S, we're just multiplying them together. So this product would be equal to 6 in this case. However, here we define S to be the set of integers x, following this condition where both x and x plus 1 are relatively prime to n. And we want to show that this is true. So this is a very daunting problem at first, especially if you've never done many proofs before, and this is certainly not a very easy proof at all. But if we know inverses and we know some facts about GCD and relatively prime numbers, we should be able to solve it. So I'm going to introduce you to a trick that we're going to use in this problem called pairing. So we should notice first that this 1 right here, 1 mod n, this is a very suspicious number because we know that two inverses, when you multiply them, like a times a to the minus 1, this is congruent to 1 mod n. So this might give us a hint that perhaps if we can pair numbers together somehow within the set S, we can actually get this to be true if we multiply them all together. So we know that if x is in S, if x is inside of S, x and x plus 1, these are both relatively prime to n. And if we want to pair these, we want to show that the number, the inverse of x, so x to the minus 1, the multiplicative inverse of x mod n, is also going to be in the set S. So that would imply that we need to show that x to the minus 1 is in S, and then x to the minus 1 plus 1 is also in S. Essentially, both of these numbers have to be relatively prime to n. So if we can prove this, then we can pair the number x and x minus 1 together, and when you multiply these mod n, they just reduce to 1. So that's going to be our goal right now. So first, let's try to prove, this is going to be want to prove. We want to prove that x to the minus 1 is going to be relatively prime to n. So we want to show that this is true. And one way we can actually do this is we can look at multiplication. So we know that GCD of x times x to the minus 1. Remember, this is an actual number, not a fraction. But because of our previous theorem we just proved right here, this theorem where we can take mods essentially in GCDs, because of this, we actually know that this is going to be an expression which is going to be equal to GCD of 1 comma n, which is equal to 1. And that's because x times x to the minus 1 mod n is congruent to 1. And so we know that this expression is going to be equal to 1. And we also know that we're given in the problem that because x is going to be an element of S already, the GCD of x and n is also 1. So because x and n share no common factors, if we were to multiply a number x to some other number, then the only factors that it could possibly share with n, so x times some number a, the only factors it can share with n have to come from the a, because x shares no common factors with n. So in this case, the GCD of x times x minus 1 comma n, because we're multiplying x by x minus 1, the only possible divisors that these share have to come from the x to the minus 1. So this is going to be equal to GCD of x to the minus 1 comma n. And because we have this equation above, we know that therefore the GCD of x to the minus 1 comma n is going to be equal to 1. So therefore we have just proven that this is the case. So now we are left to prove that x to the minus 1 plus 1 is also co-prime to n. So now we want to prove that is equal to 1. And we can actually approach this in a very similar way to how we did this one. Essentially, we want to look at the expression x times x to the minus 1 plus 1 comma n. And inside modular arithmetic, this expression would be congruent to, because we just distribute these, x times x minus 1, that's 1, plus x times 1 is just x mod n. So this is just going to be equal to the GCD of x plus 1 comma n. And because, remember, x is an element of S, we're assuming x is an element of S. So then x plus 1, we know by the condition of the problem, here, that both x and x plus 1 are relatively prime to n. So x plus 1, the GCD of this and n is also going to be equal to 1. And like our reasoning from above here, our reasoning here regarding the factors of x, we know that if any factors were to be shared between x times a and n, the factors would be from A because x is relatively prime to n. And so this GCD is going to be equal to the GCD of just x minus 1 plus 1 comma n, because x shares no common factors with n. So all the factors that they share have to come from this term right here. And so because we've proven using the mod theorem that this is equal to 1, we have that this is also equal to 1. So we can prove that this is true. And so what does that tell us? Going back to our problem up here, this tells us that if we have a number x inside of a set of S, the number x to the minus 1, the multiplicative inverse of x, is also going to be inside the set S because both of these numbers are relatively prime to n. And so if we had a set, let's say we have a set of numbers, something like maybe x1, x2, maybe there are m numbers in here. In this case, if we were to take a look at the number x1, because of what we just proved, there should be some other number inside the set where that it's the inverse of x1 to the minus 1. So some number here is going to be equal to x1 to the minus 1. And so if we were to multiply all these numbers together, we should, if we pair these correctly, we should get that the product is congruent to 1 mod n. And this is a good assumption to make, but there's one thing we're overlooking here, and that's if there's a number x where x is actually equal to its own inverse, meaning that in mod n, x squared is congruent to 1 mod n. So we actually don't know if there exists a number here, because if there is, and we pair it with itself, we're actually overcounting our product by that x. So we have to somehow address this x squared here. And we're going to do that by looking at GCD of x plus 1 and n. So we know this is equal to 1 because x is an element of S. And so let's add the expression 2x plus 1 to both sides of this congruence right here. So we have x squared plus 2x plus 1 is congruent to, and then 2x plus 1, if we add it to 1, we get 2x plus 2. That's 2 mod n, right? And we can factor both of these into x plus 1 squared. It's congruent to 2 times x plus 1 mod n. And remember, because x plus 1 is co-prime to n, we actually know that there exists an inverse for x plus 1. So if we were to multiply both sides of this congruence by the inverse, we'd get rid of this squared and we'd get rid of this x plus 1 term right here. And we would get that x plus 1 is congruent to 2 mod n, and that x is congruent to 1 mod n. And so we've just proven that if there was a number x like this, we wouldn't actually overcount because the only possible x is equal to 1 mod n. And x squared is just the same as x. So we would not overcount our product. And so by pairing all the numbers with their inverses, we can prove that the total product of all the numbers in the set S, the product is going to be 1 mod n. So that's how we prove this. And so I think this is a very complicated proof, especially if you've just started learning how to write proofs. But the main concept I wanted to show in this problem is that we're able to pair numbers. So if they give you a set of numbers and they want you to perhaps simplify the product or simplify the sum, try pairing the numbers in special ways where you're able to cancel a lot of numbers out. So in this case, multiplying by the inverse cancels the entire expression to just 1 mod n. And that's the thing we had to notice in order to approach this problem. Once we know perhaps how to approach the problem, next we can start looking at what we have to prove in order to show that we can do this. And in that case, all we had to do was show that some of these numbers, x to the minus 1 and x to the minus 1 plus 1, we had to show that both of these numbers are actually relatively prime to n as well. And by doing that, we show that we can use this pairing strategy. And so I did write this proof in a bit more detail probably on the handout. So if you're a bit confused here, or maybe you get confused later on, you can refer to the handout and see how to do it there. So now we're going to move on to theorems again. We have a lot of content to cover, and I don't think we're going to cover everything. So if you do have time and you want to learn more about higher level number theory, I really recommend looking at the handout I wrote. And so we're going to talk about binomials now. So if you're not aware what a binomial is, the expression p choose k. So let's just assume these are two random variables for now. This is going to be equal to p factorial divided by p minus k factorial times k factorial. Essentially, it's in terms of combinatorics, it's how many ways you can choose k items out of p total items, not included in order. And so binomials have a lot of things to do actually with algebra, because whenever we do an expansion, when we have two numbers like a plus b to the power of some n, we get a lot of binomials in this term. And the theorem for this expansion is called binomial expansion. So that's a pretty good hint as to why binomials are actually quite relevant in a lot of fields of math. So here we're going to analyze some binomials in regards to primes. So for a prime number p, the theorem states that p choose k is congruent to 0 mod p for all values of k between 1 and p minus 1. And so actually glancing at this at first, it's kind of complicated to see how we would actually analyze this. But if you actually look at this expression right here, it's pretty easy to see why this expression is divisible by p. And that's because p occurs only once in the top factorial here. Remember, p is a prime, so it has no divisors smaller than itself. And that means that we have one factor of p on the top. However, down here, both factorials are smaller than p by the definition of k. So both of these terms here don't have a factor of p. And so because there are no factors of p in the denominator, when you simplify this to an integer, remember, binomials are always integers. Always integers. So then we know that this integer has to have a factor of p from the numerator. And so because p divides this binomial here, we know that the binomial is congruent to 0 mod p. And so that would be our proof here. And of course, when you write it formally, you'd have to write it all out and not just like point around and explain it. But that's essentially how we're going to look at it. We're going to look at the factors on the top and bottom, and we see that p divides this expression. So knowing this theorem, we can actually prove a slightly more useful theorem here. So for two integers a comma b and a prime number p, we have that a plus b to the power of p is congruent to a to the power of p plus b to the power of p, modulo p. And so we do this by looking at binomial expansion. Because when we expand this, we have a to the power of p plus, and then p choose 1 times a to the power of p minus 1 times b plus p choose 2 times a to the power of p minus 2b. We add this all the way down to p choose p minus 1 times a b to the p minus 1 plus b to the p. And I really hope you do know what binomial expansion is. And so if we look at these terms here actually, and we look at it inside mod p, we see that by this theorem, all of these expressions right here, all of these binomials, they all have a factor of p inside, and they're all congruent to 0 mod p. So if we take this entire binomial expansion we have right here, and we take it mod p, all of these become zeros, and all of these nasty terms involving a and b here, they all are multiplied by 0 and reduced to 0. So in terms of mod p, we have that this is congruent to just a to the p plus a whole bunch of zeros. These are all zeros. And then plus b to the power of p, mod p. And so thus we've proven our theorem. So given this, we can actually extend this a bit further to multiple variables. Before we do that, I think I'm going to introduce a quick concept in proofs. So many of you have probably heard of this strategy already, but to the few who haven't, there's a technique in proofs known as induction. And essentially what we're doing is we're going to first prove that some statement. So we have a statement. So we have a statement, and we're going to show that it's true for some small number. So maybe true for some number like 1 or 2. And then we're going to assume that it is true for some variable, let's say n. So we're going to assume it is true for some variable n. And we're going to use algebra or some whatever mathematical arguments we have to prove that if we know n is true, then n plus 1 is true as well. And so because of that, we can start off saying 1 is true. Thus, if 1 were n, 2 is true. And then using the same thing, 3 is true, 4 is true, until we know that every single number possible is true. And thus, we can prove the statement. So a lot of teachers, when they first teach induction, they always talk about how it's related to dominoes, because when you push one domino down, you just cause the other dominoes to fall. That's a really bad drawing, but these are dominoes. And so I'm going to show you an example real quick. We're going to quickly prove the theorem. This is a formula that everyone should know. The sum of numbers 1 plus all the way to n, so 1 plus 2 plus 3 plus 4 all the way up to n. This is going to be equal to n times n plus 1 over 2. So we're going to try to prove this in induction real quick. So our base case, this is called a base case with a small number. Let's say that n is equal to 1. In that case, 1 should just be equal to 1 times 1 plus 1 over 2. And this is just equal to 1. So this is true. So we've proven our base case already. So now we can assume that it is true for this value of n. And we want to prove that it is true for n plus 1. So how we do that is, let's say we have this. It's going to be equal to n times n plus 1 over 2. So we assume this is true. And let's add n plus 1 to both sides. So plus n plus 1. And if we do the math here, we have that by factoring, we have n plus 1 times n plus 2 over 2. And so thus we've shown that this statement is actually true also for not only up to n, but also up to 1 plus all the way to n plus 1. Because in this case, n plus 1 and then n plus 1 plus 1 is this. So we've proven that this step is true, and thus we can complete our induction and say that it is true for all values of n. So that's how we can prove the theorem right here. So this is the idea of induction, and we're going to use it for our number theory again. So remember, we just proved in the previous problem, so I believe that's probably theorem 3.2. We've proven that for two numbers a and b, a to the power of p plus b to the power of p is congruent to 0 mod p, and then p is prime. So let's use this theorem to try to prove this more generalized theorem where we have a lot more variables. So we're going to use induction. We're going to assume that this is true for a very basic case. So in this case, let's say that it is true for n equals 2. So this is our base case. It's going to be true for n equals 2, meaning we want to prove that this is going to be congruent to a1 to the p plus a2 to the power of p mod p. So this is actually true because we've just proven it in theorem 3.2 using binomials. So we've proven our base case. Let's assume that it is true for n number of variables now. So a1 plus an to the power of p is congruent to a1 to the power of p plus to an to the power of p mod p. So let's assume this is true. Now, let's look at the expression a1 plus all the way to an plus 1 p, right? Now this expression is just going to be equal to, over here there's actually an an plus. So we have our previous sum here plus an plus 1 to the power of p. And if we use binomial expansion, actually no, not binomial expansion, if we use theorem 3.2, instead of setting two variables to be a and b, we set this sum right here to be a and an plus 1 to be b. So in that case, my bad. I actually miswrote this. This should be a plus b to the power of p. My bad. So that's the same as our base case. So in this case, we have that a and b are going to be our sum and then an plus 1. So thus we have that this is going to be equal to a1 plus an to the power of p plus an plus 1 to the power of p, right? Using theorem 3.2, we can show that this is true. So using our assumption, actually, our assumption shows that in mod p, this term right here, this entire term is going to be congruent to the sum of the powers here. So in mod p, this is going to be congruent to a1 to the p plus an to the p plus an plus 1 to the p, and then mod p. So thus, we've proven that this sum up for n plus 1 variables is going to be congruent to the sum of the individual powers of the n plus 1 variables. And that's the next step in our induction. So thus, we can conclude our induction. So we can end our induction. And we have proven this theorem. And just as a bit of a lighthearted side note, this theorem is known as freshman's exponentiation. And that is because there's a stereotype that freshmen are all bad at math. So when a freshman first enters a math class and he has to deal with this expression, not inside of mod p, just regular math, he doesn't know binomial expansion or any type of expansion. So he just directly writes this expression on the right. So that's actually why this is called freshman's exponentiation, because without mod p, this is obviously false, and that's an error a lot of freshmen would commonly make. So now we're going to talk about exponents. There's a theorem known as Fermats' little theorem. So basically, for a prime p in an integer a, we have that a to the power of p is congruent to a mod p. So you can verify this for a lot of numbers. I'm not going to bother verifying it this time. But we're going to try to prove this now. So the proof is actually very simple because we've just covered the several ingredients we need to prove it. So we're going to use induction actually for this theorem as well. So essentially our base case, we're going to assume that a is equal to 1. So base case, we're going to assume a is equal to 1 for our base case, meaning that 1 to the power of p should be congruent to 1 mod p. And this is very true. So we can continue on. I'm going to assume that, let's say, assume it is true for some value a. So a to the power of p is congruent to a mod p. Now, I'm going to prove that a plus 1 to the p is congruent to a plus 1 mod p, and then we're done. So how we're going to do that is we're going to look at a plus 1 to the power of p, and we're going to use that previous theorem we had, either the longer version, we can use this version, or we can use this version right here. But either way, we have that this expression is just congruent to a to the power of p plus 1 to the power of p, which is just 1. And by our inductive hypothesis, the assumption we made right here, a to the power of p is congruent to a mod p. And so this is just congruent to a plus 1 mod p. And so we've proven the next step, which is for a plus 1. And thus, we can end our induction, and we've proven this theorem. So I'm going to talk a bit about how this theorem might be used in competitions. This theorem is often used if you have an exponent you need to evaluate or something like that. So you can use this theorem to find out maybe there's a cycle somewhere. So it's easier for you to compute larger exponents or find other exponents. Yeah, so actually, I forgot to mention this earlier, but if you have any questions, please feel free to ask our TA, Naveen. He should be on. And you can ask him questions if you have any. You can ask him anything. Just don't spam him, please. He always complains about that. And we can move on to a theorem known as Wilson's theorem. So for a prime p, we have that p minus 1 factorial is congruent to minus 1 mod p. So this actually does seem like a very useful theorem regarding factorials in mods, but we're going to talk more about its proof for now. So in terms of a proof, we want to somehow prove that this is going to be congruent to minus 1. And it might not be immediately obvious how we're going to prove this because we can't really use some exponent trick we had before. But in fact, this is actually what we're doing here, this factorial, is we're just multiplying the numbers 1 times 2 times 3 times 4 all the way to p minus 2 times p minus 1. And this is going to be congruent to minus 1 mod p. And minus 1 is not as nice as the number 1 as we had in the previous example problem, but negative 1 is still very nice. So we should suspect that something suspicious is going on maybe in terms of pairing. So the strategy we're going to be using is, once again, pairing. So in this case, we're going to try to see how we can pair numbers in here to get -1. And you can actually see this -1 could potentially come from p minus 1, because p minus 1 is congruent to -1 mod p. So furthermore, this gives us better motivation to use pairing, because p minus 2, let's say for odd primes, p minus 2 is going to be, well, p minus 1 here is going to be an even number. So let's see what we can do in terms of pairing. Because potentially we could pair the numbers from 2 to p minus 2, and that's an even number of numbers. So in this case, we should have that maybe there's an inverse here. Maybe we can find inverses of some number here, like 2 should have an inverse somewhere. And if we can prove that, we can pair all of these to be congruent to 1 mod p. And so all we're left with is a -1 mod p. So that would prove our theorem. So we actually know that because these numbers are here and p is a prime, remember p is a prime, so all numbers in here, they should all be co-prime with p, meaning they share no common factors. So any number like 2, for example, 2 has an inverse that definitely exists because 2 is co-prime with p. And thus, we know that inside this range from 2 to p minus 2, there is a number in here where 2 multiplied by that number is congruent to 1 mod p. So all we have to do is pair all of these numbers with their inverses. And thus, the product of all these numbers should be congruent to 1 mod p. And so we finish our proof, because then we multiply by p minus 1, and we get -1 mod p. So yeah, this is actually a lot simpler than the example problem we did earlier. That one was an actual problem. This one is very simple. We just pair inverses, and we know they exist because p is a prime number. Let's see. Our next theorem we're going to show is Eulers Theorem. So this is a very popular theorem for competition simply because of how versatile it is. I'm going to mention right now, we're going to what the totient function is. Essentially, the totient function, this is the Greek letter phi. Phi of n is equal to the number of integers less than n that are relatively prime to n. So for example, we calculated this in the introductory class, but phi of 100 would be equal to 40. So that allows us to find cycles mod 100. And also it's worth noting that phi of any prime number, because all numbers less than p are relatively prime to p, this is just going to be equal to p minus 1. So in fact, if we can prove Euler's theorem, we can actually show that for prime numbers, a to the power of phi of p, which is p minus 1, is congruent to 1 mod p, if a is not 0 or p. And in fact, this is just the same expression that we actually have in Fermat's little theorem. So Euler's theorem completely generalizes Fermat's little theorem. So let's try proving this now. So the proof that we use, it's not going to be a pairing strategy this time, but we're still going to analyze a set of numbers. So we're going to find a set S as the set of numbers where the number is co-prime to n. So sets of numbers x1, x2, let's say there are m of them, and each of these numbers are going to be co-prime to n. So any xi is going to be co-prime to n. And now we're going to look at a cool trick. So we're going to multiply all the numbers in S by our number a. So we're going to assume a is co-prime to n as well. So if we multiply all the numbers by a, we have ax1, ax2, all the way to axm. These numbers should all still be relatively prime to n, because when we multiply two relatively prime numbers to n to each other, they're still relatively prime to n. And furthermore, we can actually show that all of these numbers are distinct, meaning that we're not going to have something like ax1 is going to be congruent to ax2 mod n. So nothing like this will ever happen. And that is because a is co-prime to n. So if we multiply by the inverse, we have that x1 should be congruent to x2. And assume over here, when we define set S, we're assuming all of these are going to be distinct. So we can prove by this statement right here we show that all the numbers in this set are also distinct. So let's call this set set S prime, meaning changed S. And this is neat because all of these are distinct. All of these are co-prime to n. And since we know that all the co-prime numbers to n are in S, all of these numbers should be congruent to a number inside S. So these two sets are essentially congruent in terms of their elements mod n. So their elements are all congruent mod n. And you're not going to have x1 is congruent to ax1 necessarily. x1 might be congruent to axi for some value I. And now what we're going to do is we're going to look at the product of all the elements in the sets. And first of all, we're going to know that the products should be the same because we know that the elements are all congruent to each other. So the product x1 times xm should be congruent to ax1 multiplied to axm and mod n. And if we factor out the a from each of these factors, this is congruent to a to the power of m times x1 multiplied to xm. And remember, since x1 multiplied up to xm, this is a still relatively prime number to n. So this expression has an inverse. So if we were to multiply both sides of this congruence by the inverse, we would get rid of all of these x's, and we're left with 1 is congruent to a to the power of m mod n. And m is the number of elements we have in set S. And by the definition of the totient function is a number of integers that are co-prime to n less than n. And that's exactly what m is. So in this case, m is equal to phi of n. So thus, we've proven that a to the power of phi of n is congruent to 1 mod n. And so that's how you prove Eulers theorem. So in this case, the strategy we used wasn't pairing, but rather it's looking at two sets and showing that by doing some property onto the set, doing some transformation, we actually have the same set. And we take advantage of that to get these powers of a, and we're able to prove the theorem of that. So that's a strategy I'd like to demonstrate in this problem. And we are moving kind of fast because we are running out of time. I'm definitely not going to be able to finish all of these topics in the next 15 minutes or so. So I'm going to try to finish talking about order and maybe generators by the end of this lesson. So here we're going to talk about the definition of order. So the order of an integer a in mod n is defined as order of n a is equal to k, where k is the smallest positive integer such that a to the power of k is congruent to 1 mod n. And this is related to Eulers theorem because we know that if a is co-prime to n, a to the phi of n should be congruent to 1 mod n. This is a 1. So, however, that does not mean that there does not exist a small exponent here where this is also true. So essentially, this is assuming that a to the order of n of a is congruent to 1 mod n, and there is no smaller exponent where this is satisfied. So I'm going to introduce something known as a proof by contradiction. And I'll explain what that means in a second. So a proof by contradiction is essentially a technique in proofs where instead of proving something is true, like say we're given a statement, we're going to show that if the statement is not true, so if statement false, then there's going to exist a contradiction somewhere in mathematics. So either some equation is going to not work out, or we're going to get something like 1 is equal to 2, something that's not true. And thus, the statement can't be false, so the statement is true. And that's a method we can use to prove things. So let's see. I have a theorem here. We're going to use proof by contradiction on this theorem. So for co-prime integers a and n, the order of a mod n is going to divide phi of n. So this does seem obvious at first because remember, by Eulers theorem, this is true. And if we have another exponent, it might be logical to think that that cycle, that exponent multiplied by an integer should be phi of n. But we can't be sure that there exists a separate cycle inside of this cycle. So we're going to prove this rigorously using a proof by contradiction. So we're going to assume that instead it is not divided. And remember, we can write this division as phi of n is congruent to 0 mod and then order of n of a. So that's what the statement is saying. So we're going to assume that it's not congruent to 0. In other words, we're going to assume the contrary. Assume contrary, which is basically the false of the statement. We're going to assume that phi of n is going to be congruent to some integer k mod the order n of a, where k is going to be some number greater than 0, but then less than order. So something between 0 and this, where it is a positive integer. So essentially what we're saying is there is a remainder that exists when we divide phi of n by the order. And using the definition of congruence, we're able to write that phi of n should thus be equal to order of n of a times some integer, let's say b, plus k. Because when we divide this, there's a remainder of k. And so let's put this into Euler's theorem real quick. If we substitute phi of n into phi of n here, we have that a to the power of order n of a times b plus k is congruent to 1 mod n. Now, if we use our well-known exponent rules here, we can break this into a to the order of n to the a to the power of b multiplied by a to the power of k. And because of the definition of order, this should be congruent to 1 mod n. So we have 1 to the b times a to the k, which is congruent to a to the k. And by Euler's theorem, this is congruent to 1 mod n. Now, there doesn't seem to be a very big problem at first, but if we notice the definition of k, remember, we define a k as between 0 and strictly between 0 and order of n of a. So because there exists this k where a to the power of k is congruent to 1 mod n, this defies the definition of what order is. Remember, order is the smallest integer where this expression is true. But we just showed that there is a number k smaller than the order where this is true. And thus, that is a contradiction of the definition of order. So that's a contradiction because this is not possible. There should not be a k that can do this. And so thus, we can prove that this is true. So this is what a proof by contradiction is. And essentially, it's a method that's relatively used commonly for many proofs, actually. So it's something good to know. And now we're going to actually do an Amy problem. And I'll just remark quickly that this problem was actually a number 14 on last year's Amy. So it's not supposed to be a very easy problem, but it's going to be pretty easy if we are familiar with the things that we just talked about. So I don't know how much more I'm going to get in the class. So I'll give you maybe half a minute to think about this problem before we talk about it together. And I do understand that we are moving through a lot of this content really quickly, and I doubt that this much content will usually be taught in a 1-hour lecture. So if you are confused by anything, maybe jot it down, and then you can refer back to the handout or to this video later on, because we'll post it on YouTube, we'll post the handout on our website, and you can try to learn it and truly understand what's happening there, because there is a lot of content that I am talking about. This is certainly not a very easy class. So let's dive into this problem now. So find the least odd prime factor of 2019 to the power of 8 plus 1. So we're trying to find, usually we find a large prime factor, but in this case, we're finding the least odd prime factor. So let's assume that there's a prime number p. And we're going to assume that p divides this expression. So p divides 2019 to the power of 8 plus 1. In other words, in modular arithmetic, we can write that 2019 to the power of 8 is congruent to minus 1 mod p. Really, it's plus 1 is congruent to 0, but I just moved the 1 over to this side. And so you should know that if we square both sides of this congruence, we have 2019 to the power of 16 is congruent to -1 squared, which is 1 mod p. And so we know that a cycle here occurs. And furthermore, if this 16 should be the order of, so we should have this is true, order of p of 2019. Because this is at least a multiple of the order, and no divisors of 16 satisfy this, because remember, the largest divisor of 16 is 8, and 8 does not satisfy it being congruent to 1 mod p. The smallest one would therefore be 16, so the order of p of 2019 is 16. And so we can use this fact now to make some generalizations about what p could possibly be. Because remember, by Euler's theorem or Fermats little theorem, we know that any number a to the p minus 1, because remember, phi of p is equal to p minus 1. So a to the power of p minus 1 should be congruent to 1 mod p. And because of our theorem we just proved, where order divides phi, we know that order of p of 2019, which is equal to 16, should divide phi of p, which is going to be equal to p minus 1. So we should look at primes where p minus 1 is divisible by 16. So the first one that's obvious is p equals 17. Now this is where you have to do some computation. This is an AMY number 14. You can't expect it to be relatively computationless. So if we do the math and we calculate what 2019 to the power of 8 is, we don't actually calculate this. We calculate it mod 17. So that's a lot easier. We actually get that this is not congruent to -1 mod 17. And remember, we are only assured that the order is 16. We don't know if this is actually -1 based on this expression here. So we have to keep testing primes. But luckily, the next prime is going to be 97. So 97 that satisfies 16 divides p minus 1. And if you do test out 2019 to the 8 mod 97, you actually get that this is congruent to -1. And so the smallest prime factor would just be 97. So if you actually knew about order and you knew about these number theory rules and you had some intuition, this number 14 AMY problem is actually considerably easy for number 14. So that's probably the extent to where these type of theorems and properties would actually come into play in computation. I have a bit more time. I'm going to quickly talk about what generators are, because this property, this is a term that people refer to a lot in higher level number theory, but for multiple subjects. So we call a generator zeta. So this is the Greek letter zeta. And usually for handwriting, I write it like this. But it's up to you how you want to write it with your hand, but this is just how I write it. So a generator zeta modulo n is an integer for which every other integer a co-prime to n, there is an integer k such that zeta to the power of k is congruent to a mod n. So that's a very complicated definition, but I'll explain it quite simply. So we have a number zeta, and by taking an exponent of zeta, for example, zeta to the power of k, we can actually produce every single co-prime number to n. So that's what a generator would be able to do. It's able to generate every single co-prime number to n. And you have to imagine these numbers are quite special, and they should remind you of primitive roots of unity from complex numbers. For example, e to the I pi over k, because these are able to generate other roots. But we're not talking about complex numbers here, we're talking about mods. And in mods, actually, these are known as primitive roots, modulo n. And there are a bit of rules on how you can define this here and there, but in general, if it's a generator, usually it'll be a primitive root mod n. And so we have time to talk about one theorem real quick. This is a theorem that'll help you define if number is a generator or not. So an integer zeta is a generator if and only if the order of zeta mod n is equal to phi of n. So remember, order always divides phi of n. So in this case, we're saying that it's not a divisor of phi of n less than phi of n. It's just phi of n itself. So the way we can prove this, this can be proven using a simple argument of generators. So I'll show you real quick. Because this is a generator, we have to be able to generate with this exponent. We have to be able to generate exactly phi of n distinct values using this expression mod n. Because a generator has to be able to create coprime values a. Every coprime value a must be generatable by zeta. So there should be phi of n different exponents for k. And so that's how we can show that if this is a generator, its order has to be phi of n. Just remember, if its order was smaller, we would be repeating values of a in between, and we would not be able to generate all phi of n coprime numbers to n. So that's how we prove the if direction. And if we prove the backwards direction, and we're given that order of zeta is equal to phi of n, we can show that zeta is a generator, because when you take zeta to the k and you run it from 1 all the way to the order, then you should be able to generate every single distinct value that is coprime. Because if you were to loop back to a previous number, it would no longer be a distinct value that's coprime. So that's how you'd prove it. And I do have a more rigorous proof written on the handouts. So if you are interested more in these, look on the handouts. I also do talk about quadratic residues. Essentially, we do discuss solving this congruence. X squared is congruent to a mod n. We discuss this a bit more in detail. And yeah, so we did cover a lot of things in this class. But if you want to learn more, check out the handouts. And someone asked me, can I suggest a book over number theory about this? There are a lot of books out there. One book I can probably think of is, this one is a bit more advanced. There's something called Intro. You can search up Intro to Number Theory, and there are probably a lot of books about it. And an especially higher level book is by this guy called Apostle, but this one is quite difficult. So of course, you can always look at other sources, AOPS. You can look at the handouts we have. And if you do want to learn more about number theory, I actually have written a large PDF book-styled like lecture document about number theory. And if you want to contact me on Discord or some other method, you can ask me, and I might be able to share some sections of it with you. And so thank you for attending today's class. And also check out our AOPS forum. We do have a forum up there. If you want to ask questions with LaTeX or anything, make sure you check that out. And I believe our TA has attached our Discord link in the server. So thank you for coming. You guys are free to leave now. And if you have any questions, ask it real quick. I'll end our video lesson in maybe half a minute or so. What books was I saying? Okay, to be more clearly, I'll try to find the book, the links to the book, and I'll post them on the Discord intermediate channel in a short moment. So just check the Discord whenever you can, and I'll try to post some materials on there if you are curious more about number theory. All right, I'm gonna end our class now. Thank you for coming, everyone.